We've all seen neural nets in action doing some amazing things. Under the hood, these are just a series of matrix multiplications where the output from one operation is passed to another. The power of a neural net is determined by the number of matrix multiplications and the size of these matrices. Matrix multiplication in itself is a computationally intensive operation, and the cost increases dramatically with the size of these matrices. For a really long time, this was a big issue that limited the application of neural nets. Then in 2007, NVIDIA released CUDA and changed everything. For large matrices, the speed up from GPUs can be as high as 2000%. In this video, I will explain how to write code for a GPU by answering 4 simple questions. What is the big picture difference between a CPU and a GPU? Why do applications run faster on a GPU, and can a GPU speed up anything? How can we perform matrix multiplications on a GPU? And finally, are we getting the best out of the GPU? So, without further ado, let's get started. A matrix can be seen as a 2D data structure. It has rows indexed from 0 to n-1, and similarly columns are also indexed from 0 to n-1. For simplicity, I'm assuming the same number of rows and columns, but they can be different. This indexing allows for easy identification of the matrix elements, where the first number in the subscript represents the row index and the second number represents the column. The multiplication of two matrices results in another matrix. The element 0, 0 of this matrix is calculated by performing the dot product of the first row of the first matrix and the first column of the second matrix. In the dot product, the respective elements are first multiplied and then all of them are added together. Similarly, element 0, 1 is calculated using the first row and second column of the two matrices. This goes on for all the elements. I wrote a simple program in C to perform matrix multiplication. Inputs to this function are pointers to matrices A, B, and C and the size of each matrix, which is same in this case. This program will run on the CPU, which has a few cores. As I'm not doing anything special here, the CPU will spawn a single thread. A thread can be seen as an individual worker, and the execution of a thread is sequential as far as a user is concerned. This thread's first task is to evaluate the first element of the matrix C. A nested loop in the program loops over all the rows in the A and columns in the B. For the first combination of row and column, the program again loops over the elements and multiplies them, finally adding them to the total. The result is then stored in the matrix C. The thread then moves over to the next element and performs the same operations. It is important to note how the program loops over the rows and columns one by one. Looking at this, you can imagine that matrix multiplication is computationally intensive. In fact, if you run this program for n ranging from 1000 to 8000, you will see the execution time increase drastically to almost 30 minutes for the matrices of size 8000. This is not good. However, if you look carefully at the algorithm, the evaluation of any element of matrix C does not depend on others. Just look at the first row of C. Each of those elements can be computed independently. The same thing applies to all the other elements of C. GPUs are especially adapted to these type of computations where n can be quite large because the hardware contains thousands of cores for parallel execution. These cores can spawn many threads and each can execute an operation independently. So if we have 2000 by 1000 matrices, a GPU can easily spawn 1 million threads, and each thread is responsible for computing a single element of the output matrix. It will retrieve the corresponding row from matrix A and a column from matrix B, then do the matrix multiplication plus addition by looping over the elements. All workers will do this independently and simultaneously, reducing the computation time significantly. Before I delve into the code, let me give a very high-level overview of CPU and GPU hardware. CPUs and GPUs have execution units called cores that perform the arithmetic operation, and an off-chip memory unit, RAM and VRAM respectively, to store the required data. The big difference is that a CPU has much fewer cores than a GPU. A GPU can't function independently. It's the job of a CPU to move data between RAM and VRAM. In other words, a CPU can be seen as an instructor who manages most of the tasks and is responsible for assigning specific tasks to the GPU where it has an advantage. Mind you, CPU architecture is far more complicated than this. But to keep things simple, I decided not to discuss other components like cache, control unit, etc. The same applies to the GPUs, but I will cover the details of GPU hardware in another video. For now, understanding this much is sufficient. I'm using NVIDIA's CUDA platform for programming on the CPU and GPU cores. More specifically, I'm using CUDA C, and the program here reflects the presence of both a CPU and a GPU. When the execution starts, there is a single thread. This thread loads data into RAM and then allocates space on the VRAM before moving the data there. It then calls a kernel function which defines the executions to be performed on the GPU, and at this stage multiple threads are generated on the GPU. Each thread computes the same kernel function in parallel and stores the results back in the VRAM. The CPU thread then fetches the results from VRAM and puts it into RAM, where the user can either print the results or perform further operations. Let's now look at each of these steps in detail. At the start of this simple C program, I randomly initialize the input matrices and allocates memory for the output, which is all done on RAM using a single CPU thread. Before copying matrices A and B from RAM to VRAM, host code allocates memory for the 3 matrices on VRAM. This is done using CUDA malloc function. This function accepts 2 parameters. The first parameter is the address to the pointer variable for the select matrix. The address to this pointer must be cast to void because the function accepts a generic pointer, which is not restricted to a specific type. The second parameter is the size of the data to be allocated in the number of bytes. This function is similar to cmalloc, but it does not return a pointer. Instead, it accepts the address of the pointer because this allows the CUDA malloc function to return a value which is of type CUDA error T, reporting errors during memory allocation. This can then be passed to an error checking code. At this point, we have successfully allocated memory on VRAM. Once we have allocated the memory and pointers to the respective memory locations, data can be transferred from RAM using CUDA memcopy function. This function accepts 4 parameters. Pointer to the destination. When copying data from RAM to VRAM, this will be the device pointer variable, that is DA or DB. Pointer to the source. When copying data from RAM to VRAM, this will be the host variable pointer, that is A or B. Number of bytes to be copied, and finally, the transfer direction. When copying data from RAM to VRAM, this will be CUDA memcopy host to device. Note that this is a symbolic predefined constant of the CUDA programming environment. Similar to memory allocation code, this function also returns a CUDA error T value. Once the matrices have been copied, the GPU execution units will perform matrix multiplication and the results will be stored in VRAM. The same function can then be used to copy data from VRAM to RAM by appropriately defining the function parameters. The direction of transfer in this case is CUDA memcopy device to host. Now, let's look at how a GPU performs parallel matrix multiplication. For simplicity, consider the matrices of size 10. In this case, the GPU will create several threads and assign a thread to compute an element of the output matrix C. All these threads work in parallel and reduce the computation time drastically. A genuine question here is, who decides which thread works on which element? To answer this, we need to look at how threads are organized. When a kernel function is launched on a GPU, a grid is created. Inside this grid, multiple blocks are generated. Each block is given a unique coordinate. Inside a block, multiple threads are arranged with unique coordinates as well. The most important thing here is that each block must have the same number of threads and the coordinates assigned to these threads are local to the block. I'm currently showing a 1D thread layout, but the thread inside a block can be arranged in a 2D or 3D layout. Note that this will change the coordinates of the threads. Similarly, the blocks can be arranged in a 2D or 3D layout as well. In the CUDA nomenclature, these coordinates are written as Z, Y, X. Remember that this is a bit different from the standard way of writing things, and there isn't much we can do about it as it's predefined in CUDA. Applying this to an example involving 10 by 10 matrices, I first set a block with 3 threads in the Y direction and 4 threads in the X direction. Now to cover all the elements, I need to create 4 such blocks in the Y direction and 3 in the X direction. When writing this in code, I first use dim3 type, which is defined in CUDA, to set the dimensions of the block. Note that the parameters passed are in order X, Y, Z. Similarly, the grid dimension is defined using the seeding function to ensure complete thread coverage. Notice that this will create 12 threads in each direction, and while performing the computations, we need to keep this in mind and not use these extra threads. This is done inside the kernel function, so let's see how we can do that. At this stage, we have threads organized in the GPU. Each one of these threads will execute the same kernel function. For example, let's select a thread at random and pass through each line in the function. The first two lines are used to identify which element of C this thread will work on. For this particular grid, the y and x dimensions of the block are 3 and 4 respectively. This thread is located in a block whose index is 1, 1 in x and y directions. Finally, the coordinates of this thread inside the block are 1 and 2 in the y and x directions. This gives us the coordinate of the element C this thread will work on. Next, we check if this thread is within the bounds. Remember, there are 2 additional threads in each direction. Once it clears the if statement, the thread starts working on the select element by retrieving the corresponding row and column from the memory, looping over it and performing the dot product. Similarly, all threads do the same thing in parallel and return the complete matrix multiplication. Parallel programming concepts can be a bit daunting at the start. For this reason, I've also written notes for this video and uploaded them on my website. If you're interested in a more detailed discussion, you can access it for free. And if you find it useful, please subscribe. It is completely free and you'll get notified whenever I publish a new blog post, usually every 7 to 10 days. Anyways, please let me know what you think in the comments. Suggestions are always welcome as I'm trying to improve with every new upload. Thanks a lot for watching and I'll see you next time.